Okay, welcome viewers. This is Professor Engg Karimi from Jamia Millia Islamia, New Delhi, and today I'm going to discuss about Cascade System, which is a part of the Refrigeration and Air Conditioning course for BTech Mechanical Engineering students. And Cascade as such is a word which perhaps has got a meaning of one and the second one in series, so that the effect of the first is given to the second. So that is cascading effect. So this is a cascade system which is actually trying to transfer the cooling effect with the help of coupling two systems. So we already know from our basic information that there is a vapor compression system, and vapor compression system consists of compressor, condenser in sequence, expansion device and evaporator. So we have a evaporator here, we have a compressor here, condenser which is rejecting heat to the atmosphere, which can be air or water, anything, and this evaporator, which is shown with the yellow color, is absorbing a certain amount of heat, say QE1, and we have state conditions 1, 2, 3 and 4 after components. We have once again another vapor compression system, similar vapor compression system. In terms of components, we have a compressor, condenser which is going to reject heat, expansion device and evaporator. So this compressor and this compressor is different in the sense that this is a vapor compression system 1 and this is a vapor compression system number 2. So we have named vapor compression system 1 and vapor compression system 2. So WC2 represents the compressor work done by vapor compression system 2, and QE is the amount of heat which is absorbed by vapor compression system 2. So 2 represents the vapor compression system 2 and 1 is the vapor compression system 1. Now let us understand this particular thing once again with the help of the pressure enthalpy chart. Now, to make it very clear to you, we have refrigerants which are having different characteristics. So each refrigerant has got its own characteristic, and therefore as it is having its own characteristics, it will be having its own curve. So you see there is not one curve, there are two curves. One is a blue curve and the other one is a gray or brown curve. So we have two refrigerants, one is R1 and other is R2. So we have shown in our previous diagram also, vapor compression system is having R1 refrigerant in vapor compression system 1 and R2 refrigerant in vapor compression system 2. We are not having same refrigerants flowing in the two vapor compression systems because we want to choose two different refrigerants for a purpose, and therefore we are having two different refrigerants having different type of characteristics and therefore different types of characteristic curves. You see, if you see the diagram, this refrigerant, which is refrigerant number 1, is having a higher critical temperature or critical value, which is corresponding to the same pressure scale. You see, if you see the pressure scale, so this particular value of pressure is higher, very high, you see. But this critical value of this particular refrigerant R2, which is represented by brown curve, is lower. So refrigerants with two different characteristic properties will be showing its own characteristics and properties. So let us see and understand now the vapor compression system 1 and 2 on the pH chart. If we see the vapor compression system 1, then we see that it is having state condition 1, 2, 3 and 4 as shown with the red process lines, and therefore the WC1 here and QC1 and QE1 are representing here as WC1 here, QC1, that should be QC1, so this is QC1. So QC1 is the amount of heat rejected by the vapor compression system 1, and WC1 is the amount of work done by vapor compression system 1. Similarly, QE1 is the amount of heat absorbed by vapor compression system 1. Now let us think that we have to reject heat to a city which is having a maximum ambient temperature of that is the peak temperature that the city goes is 45 degrees centigrade. If we want to reject heat with the help of condenser, then we need to have a higher temperature of the coil, so that the temperature of the coil is higher than the ambient condition. That is how the coil will reject heat to the ambient or the atmosphere. So we need to have a difference of 5 degrees centigrade temperature differential. So we are having QC1 condenser temperature higher than the ambient peak temperature. So 50 degrees centigrade is chosen with the help of the ambient condition prevailing outside. Ambient peak temperature has to be prevailed outside. So corresponding to the 50 degrees centigrade chosen for condenser, we will be having a certain pressure. So we will be having this pressure, say PA. So if PA represents 50 degrees centigrade temperature for refrigerant number 1, PA is for 1. Similarly, if we choose this to be at 10 degrees centigrade, evaporator be 10 degrees centigrade, then what is this? This is PB. So what is PB? PB is going to give you a temperature. This is 10 degrees centigrade. It will go to this particular curve. Here it will also be 10 degrees centigrade, which is saturated liquid condition. This was also saturated liquid condition. So this particular pressure is corresponding to R1 refrigerant at 10 degrees centigrade. You see? Okay. Now we wanted to absorb heat, actually not from the vapor compression system R1, which is at 10 degrees centigrade. What will R1 do? R1 will absorb heat, and its coil is at 10 degrees centigrade. So whatever surrounding is there for evaporator QE1, so whatever surrounding is there for this evaporator of the vapor compression system 1 will be absorbing heat from the surrounding, which is higher than 10 degrees centigrade chosen. So this was selected as 10 degrees centigrade, and this was selected as 50 degrees centigrade, as the ambient temperature is, say, 45 degrees centigrade. So this evaporator will be absorbing heat from area which is at higher temperature than 10 degrees centigrade. So it will be absorbing heat from anything which is at higher than 10 degrees centigrade. So here this evaporator will be absorbing heat from minus 10 degrees centigrade or higher than 10 degrees centigrade. Now this is clear. So PB pressure of the vapor compression system 1, which is having R1 refrigerant, okay, will be, so you can choose anything. You can choose R134A as a refrigerant which is having 10 degrees centigrade temperature. That can be achieved with the help of R134A. Now let us now again go to the cycle number 2. The cycle number 2 is going to absorb heat, or which is having an evaporator coil temperature of minus 10 degrees centigrade. So this particular point the saturation temperature is how much? Minus 30 degrees centigrade. So this pressure, and this pressure is say PD, because this particular pressure at which the condenser of the refrigerant vapor compression system cycle number 2 is, that is at a pressure PC. So we have four pressures. One pressure is PA, which is at 50 degrees centigrade for R1. We have PB, which is 10 degrees centigrade for R1. And we have PC, which is 15 degrees centigrade for R2. PC. You see PC line? This is PC line, which is corresponding to 15 degrees centigrade, and that is for R2. And similarly, we have PD pressure, which can have values which is representing minus 30 degrees centigrade achievable saturation temperature, minus 30 degrees centigrade, and therefore we are having a temperature which can be minus 30 degrees centigrade. So what will happen is, the refrigerant number 2, R2, sorry, this is R2 already there. So refrigerant number 2 will be absorbing heat from anything which is higher than minus 30 degrees centigrade. So anything which is at minus 25 degrees centigrade, any space, a space to be cooled. Supposing there is a space which is at a temperature of minus 25 degrees centigrade, it will go on giving heat. So the evaporator number 2 will absorb heat from minus 25 degrees centigrade temperature, because the coil temperature is set at minus 30 degrees centigrade. So this heat will be absorbed and the compressor will do its work, and the condenser of R2, that is vapor compression system number 2, condenser number 2, will reject heat at 15 degrees centigrade. So when it is at 15 degrees centigrade, anything, I repeat, when the condenser of vapor compression system R2 is set at 15 degrees centigrade, so what will the condenser do? Condenser will reject heat to a space which is at lesser than 15 degrees centigrade. So if the temperature surrounding is 20 degrees centigrade, it will not be able to reject heat. So if we take this condenser and send it to the ambient temperature is 40 degrees centigrade, and here it is maximum that it can go is 15 degrees centigrade. Can it give away the heat? It will start absorbing heat because the ambient temperature is 45 and this is 15 degrees centigrade. No, it cannot. So this 15 degrees centigrade temperature of the condenser can reject heat only to some space which is lesser than 50 degrees centigrade. So what we are going to do is that we have to have a space which is shown by this shaded area, which is insulated. Okay, so this condenser, which is going to reject heat at 15 degrees centigrade, should look for a surrounding which is lesser than 15 degrees centigrade. Okay, so this 15 degrees centigrade will look for surrounding which is lesser than 15 degrees centigrade. So obviously the above vapor compression system number 1 is having 10 degrees centigrade. So this 15 degrees centigrade will go on rejecting heat to the 10 degrees centigrade evaporator. So this condenser of vapor compression system 2 interacts with evaporator of vapor compression system 1. Condenser of vapor compression system 2 rejects heat. So QC heat is rejected, and this rejected heat cannot go out of this shaded area, and this heat will be absorbed because this is at 15 degrees centigrade and this is at 10 degrees centigrade. So heat will not escape from this particular boundary. It will be absorbed by evaporator. So this evaporator is not absorbing heat from any space but from the condenser of the vapor compression system number 2. So heat rejected from the condenser will be absorbed by evaporator. So what is happening is the heat which is absorbed by vapor compression system number 1, if it wants to get rejected, it cannot get rejected but only by be absorbed by evaporator number 1 of vapor compression system 2, which is coupled. So this vapor compression system is coupled with the vapor compression system 2. This coupling of vapor compression system is known as cascading. So if you want to cascade anything, then you have to have coupling of the two systems. So here we are coupling the two systems by how it is joined, because the heat rejected by condenser number 2 cannot go anywhere but be absorbed by the evaporator number 1. So this evaporator will be absorbing heat from the condenser, and this heat absorbed is not from any other space but here, and this heat will, when it is absorbed, it is getting rejected apart from the energy taken from the compressor work to the atmosphere. So what is happening is heat absorbed from QE2 evaporator number 2 is getting rejected finally to atmosphere. So it is absorbing heat, transferring the heat, and rejecting the heat to the atmosphere. It is not absorbing heat and transferring the heat to the atmosphere, but indirectly handing over the heat to the vapor compression system number 1, and this vapor compression system number 1, it takes that responsibility and then transfer to the atmosphere. So what is the net result of this particular cascading or coupling of the vapor compression system is that we get a cooling effect which is very low temperature, that is minus 30 degrees centigrade, and we can have a system which can be working when the atmospheric condition is 45 degrees centigrade. So minus 30 degrees centigrade cannot be achieved perhaps with the help of only one refrigerant, because the refrigerant will not have property of absorbing heat from minus 30 degrees centigrade. If you want to draw one vapor compression system, or even if you want to use compound compression, it will be not possible to have one refrigerant, because if we choose this refrigerant, for example, its limit is limited only up to this. The critical temperature stops here, but this refrigerant critical temperature stops here. So if we choose two refrigerants, then it can be coupled together to achieve a temperature of minus 30 degrees centigrade. So refrigeration systems which feels like achieving very low temperatures is possible with the help of cascade refrigeration system. So cascade refrigeration system is nothing but combination of vapor compression systems, 2 or even 3, here 2 is shown, and very low temperature refrigeration can be achieved at higher ambient temperatures, and therefore we have to select refrigerants which can solve the purpose of low temperature applications and have critical temperature values which can solve this problem. We cannot choose this refrigerant or this refrigerant for one particular purpose. We cannot achieve with the help of one refrigerant. Now talking about COP, then what is the work done? What is the work requirement in order to achieve this QE2 amount of heat absorbed? Is with the if you want to QE2 amount of heat to be absorbed at minus 30 degrees centigrade, then you have to do two work, WC2 and WC1. This QE1 is not the heat absorbed and not giving you any effect, only it is transferring. So don't talk about this. So actually what is the target is QE2. QE2 was the target, and in order to achieve that, we have to transfer QE1, which is done by automatically. But what do we have to spend in terms of money, in terms of energy, is WC2 and WC1. We cannot go ahead with only WC1 or individual WC2. We have to go with two compressors in order to transfer heat from minus 30 degrees centigrade to 45 degrees centigrade ambient conditions. So we have to have two compressors WC1 and WC2 is required in order to absorb the QE2 amount of heat, which is set at minus 30 degrees centigrade temperature. And here we have to go and find out the mass flow rate of refrigerant number 1. So mass flow rate of refrigerant number 1 here into H2 minus H1. So this is H2 minus H1, mass rate of refrigerant number 1. This is refrigerant number 1. So MR1 into H2 minus H1, WC1. Similarly, what is the amount of work done by the second one is WC2. WC2 is what? The mass rate of refrigerant number 2. So you have to see MR1, MR2. These are different mass flow rates, and these are different enthalpy values. So H2 and H1 will be different. HB and HA will be different. So we have to see that HB minus HC for refrigerant number 2 will be the enthalpy change. So if we see the COP, it will be the amount of what do we want to achieve is QE2, the amount of heat absorbed at minus 30 degrees centigrade, divided by the work done during compression, and that is the COP of the Cascade System actual. This is Professor Engg Karimi from Jamia Millia Islamia, trying to explain you what is and how does the Cascade Refrigeration System works. I hope you understand. You can always communicate with me on my mail address available at jmi.ac.in. My name is Engg Karimi. I am in the mechanical engineering department. So you can communicate with me if you have any doubts, or if you have anything to suggest, kindly tell me. Thank you very much, listeners, for being patient. Thank you very much.